Welcome, everyone, to this special explainer. Today, we're taking a massive leap forward in your development journey with a complete TypeScript crash course. Now, if you're already familiar with JavaScript, you are in the exact right place, because we're about to take everything you already know and, well, make it completely bulletproof. We're going to break this all down into clear, structured levels to help you truly master these concepts. So get comfortable because we're going to take our time today and really unpack this.
Okay, let's dive into this. Have you ever written perfectly valid-looking JavaScript? Everything seems fine, only to have your entire application completely crash the exact moment a user interacts with it? Yeah, we've all been there. That right there is JavaScript's fatal flaw. It's a wildly flexible language, but that flexibility means errors are entirely silent until the program actually runs. I mean, you can literally pass a text string into a complex math function, and JavaScript, it won't stop you. It'll just fail spectacularly when it's way too late.
So that brings us to level 1, why TypeScript?
I want you to think of TypeScript not really as a brand new language, but more as a strict super assistant. It's this incredibly powerful layer that wraps right around your JavaScript, and its entire job, literally its only purpose, is to force you to write better, cleaner, and safer code. On one side, you've got the Wild West of vanilla JavaScript. In JS, you can pass the letters A, B, C into a division function, and it fails at runtime, giving you that super frustrating not a number error in the browser. But with TypeScript, by simply defining our expected types, the compiler acts like a shield. It instantly flags the error right there in your editor before you even try to run the code. It just catches the bug immediately. It's a real game changer.
Now, you might be wondering, browsers don't actually understand TypeScript directly, right? They only speak JavaScript. So how does this actually work? Well, it's a pretty simple 3-step process. First, you write your strict code in a .ts file. Then you run the TypeScript compiler. You'll use the command tsc for that. This compiler acts as a translator, or what we call a transpiler. It reads your strict code, strips away the TypeScript-specific stuff, and outputs a standard, beautifully formatted .js file that any browser can perfectly understand. Moving right along to level 2, basic types and setup. Setting things up in VS Code, especially if you grab the Code Runner extension, gives you this magical first-class experience right out of the gate. And here are the core building blocks you're going to be working with every single day. You explicitly declare these primitives: string for text, number for math, boolean for true or false, arrays for lists, and void for functions that don't return anything. By declaring these, you unlock absolutely incredible auto-completion in your editor, because the editor finally knows exactly what data it's holding. But hey, notice that last bullet point? Avoid the any type. Seriously, at all costs. Using any completely bypasses TypeScript's safety net, turning it right back into unpredictable vanilla JavaScript. Just don't do it.
So the crucial point here is how we actually control this compiler, and we do the whole shebang using a file called tsconfig.json. This file puts you squarely in the driver's seat. You can dictate the target version of JavaScript you want output, you can organize your folders using rootdir and outdir, and, this is the big one, you can use no emit on error. This is a brilliant setting. It stops the compiler dead in its tracks if you have even a single error in your TypeScript code. It guarantees that bad code never, ever reaches your generated JavaScript files.
All right, level 3, custom types and interfaces. This is where we ramp things up.
We are moving past simple primitives here and starting to map out complex blueprints. Custom types and interfaces are essentially just that, strict blueprints for your data. Whether you use the type keyword or the interface keyword, and honestly, they're largely interchangeable, you are defining exactly what an object must look like. Say you create an app config interface, right? And it demands a port number and a debug boolean. Well, TypeScript will literally scream at you if you accidentally try to assign a text string to that port. It drastically reduces those silly typo-related bugs and structural mistakes that can take hours to track down. Building on that exact idea, we have a really unique feature called a tuple. A tuple is basically a fixed-length array where the exact data type of every single position is known completely in advance. Imagine storing geographic coordinates, like the exact location of Dhaka. You strictly need a latitude and a longitude, right? That's 2 numbers, no more, no less. So you define a tuple as number, number. You can also use this to, say, return multiple values from a single function simultaneously, like passing back both a quotient and a remainder from a division calculation. It's incredibly handy. But what happens if another developer on your team tries to dynamically push a third number into your precise 2-number coordinate array later on in the code? Well, that breaks the rules. And that's exactly why tagging a tuple, or any property really, with the read-only modifier is such an amazing safety net. Once the data is created, it's locked in for good. No one can secretly push unauthorized data into your e-commerce order items or somehow mutate your core configurations later on. It just gives you so much peace of mind. Welcome to Level 4 Unions, Literals, and Enums. Let's look at how we control exact values. Okay, so sometimes an ID in a database is a pure number, but then sometimes it comes back as a string from an external API. It happens all the time. If you force it to be strictly a number, your code is going to break the second it sees that string. But by using the pipe symbol, you create what's called a union type. So you can define your ID as string/number. This allows your functions to beautifully and safely handle both shapes of data without throwing arbitrary runtime errors. You get the flexibility of JavaScript, but with strict checks. And this brilliantly illustrates the power of enums. Enums protect your production data by restricting a variable to a predefined absolute list of options. Let's say your factory only produces red, green, and yellow t-shirts. You'd create a color enum for just those three. Now, if a tired developer accidentally tries to assign the color purple to an order, no way. The code simply will not compile. And by the way, these start automatically from 0 if you don't assign them a specific value. It completely eliminates whole categories of bad data from ever entering your system.
So just to summarize the distinctions here, because it's important. A union allows multiple different types, like a string or a number. An enum restricts a variable to a predefined named set of options, like color.red. But notice the literal types in the middle there. This is where you restrict a variable to exact specific strings. If you define an HTTP method type as literally just get or post, TypeScript will completely reject any other word typed in there.
All right, you made it to the boss level, generics and utility types.
This is where we look at the really advanced features that truly separate TypeScript beginners from the masters. Let me pose a pretty complex problem. Imagine you need to write a utility function that simply grabs the first item from an array. You want it to work flawlessly, whether you hand it an array of strings or an array of numbers. But remember our rule? We are strictly forbidden from using the anytype, because that destroys all of our safety checks. So how do we make our function incredibly flexible, but still strictly typed? The answer, my friends, is generics. By passing an angle-bracketed t to your function, you are creating a special kind of variable. But it doesn't hold data. It holds the data type dynamically. It acts like a placeholder. When you pass an array of strings into the function, TypeScript is smart enough to intelligently infer that t is now string, and it locks that type in across the entire function. So your code remains incredibly reusable, but 100% strictly typed. It's honestly kind of brilliant.
Now, what's really interesting about this slide is how we can magically manipulate existing types to save a ton of time. Let's say you have a user type that requires an ID, a name, and an email. But when someone is just registering on your site for the first time, they don't have an ID yet, right? The database is going to generate that later. Well, instead of writing a completely redundant new user type from scratch, you can use a built-in utility called Omit. You simply write omit user, ID, and TypeScript dynamically generates a brand new type for you by just dropping the ID property.
And speaking of really brilliant shortcuts, what if you don't want to completely omit a property, but you just aren't sure if it'll be there? You can simply make it optional. By just dropping a question mark right before the colon in your type definition, TypeScript understands that this piece of data might be there or it might not. It transforms a strict requirement into a flexible, optional one. TypeScript is absolutely loaded with these built-in tricks to keep your code super clean.
So from avoiding silent runtime crashes to implementing highly dynamic generics, you have officially leveled up. The fear around TypeScript, that should be completely gone now. The only thing left to do is to start integrating these concepts immediately, practice them regularly, and watch your code quality skyrocket. Because once you actually experience the safety of strict type checking, you really have to ask yourself, how many hidden bugs are lurking in your old vanilla JavaScript right now, just waiting for a user to click the wrong button? Thanks for joining me on this explainer. It's been great, and I will see you next time.